It is my pleasure to introduce our last speaker for this block is Andreas Montakis from Northwestern University. And the title of his talk you can easily see on his slide. Yes, please.
Okay, so thank you for the introduction and thank you for organizing this very nice day conference. So I will speak about basically multiplicative actions. So this is all going to be this is all based on joint work with Nikos Konstantikinakis from the University of Crete. So I work on an area called the Ergodic-Ramsey theory, which basically the main thing we study is patterns in large subsets of usually the natural numbers, or in other contexts, large subsets of groups. So I will start by an old theorem of Sur, which says that the equation x plus y equals z is partition regular. And this means exactly that if you take the natural numbers and you partition them, or you color them in finitely many colors, then one of the colors will contain x, y, and z, which satisfy the equation x plus y equals z. So this is an old theorem. It was proved in 1916. And then several years later, it was hugely generalized by Rado. And what Rado did was that he basically characterized all systems of linear equations that are partition regular. Here I have stated Rado's theorem in the special case of one equation. So Rado proved that the equation ax plus by equals cz is partition regular if and only if a, b, and c, the triple ABC, is what we call a Rado triple. And being a Rado triple means that either a equals c, or b equals c, or the sum of a and b is equal to c. And here I want to ask, is this bar? I'm seeing a bar here which has to do with screen sharing. Do you see it, or do you see the full slide?
No, full slide.
Perfect. Okay. Yeah. So here I'm saying that Rado's theorem is in fact stronger because he characterized all systems of equations that are partition regular. But for this talk, I only chose to state the one equation version. So it's natural to ask what happens with higher order equations, because here we had x plus y equals z. So one may ask, can I add squares and ask about x squared plus y squared equals z squared being partition regular? Of course, there is no point in putting x cubed plus y cubed equals z cubed or higher powers, because by this is the last theorem of Fermat, which is false, which we know that they do not have solutions at all. So we can still ask about quadratic equations. So Erdos and Graham asked for a quadratic version of Sur's theorem. Namely, they asked, can we prove that the Pythagorean equation is partition regular? And that would mean that if you partition the natural numbers in finitely many cells, then one of the cells will contain a triple xyz. So all of them will be in the same cell of the partition, and x, y, and z satisfy the Pythagorean equation. So this question was asked in the 70s. And one may also ask, what about if I put some coefficients? Namely, when is the equation ax squared plus by squared is equal to cz squared? Now, one can see there is a straightforward way to prove that if the equation ax squared plus by squared equals cz squared is partition regular. So if you have this, then the same equation without the squares is also partition regular. And this would tell me that ABC has to be a Rado triple. Namely, the easy direction of characterizing when this equation is partition regular is the following. If the equation is partition regular, then either A equals C, or B equals C, or the sum of A and B is C. So the interesting direction is the opposite. Can we prove that whenever ABC is a Rado triple, then the equation is partition regular? So this is what I will speaking about today, about partition regularity of this equation. So in the past 15 years, the previous equation and the original one, the question of Vertus and Graham about the Pythagorean triples, where A, B, and C are all one, those questions have drawn a lot of attention, and there has been very significant work of Franzikakis and Host, and later by Franzikakis, Klurman, and Moreira, where they deal with partition regularity of pairs. And there have been 3 papers I have cited here, but there are more where they all in every paper, the authors deal with pairs. So here I have decided to state one of the theorems, which was a very big result. And the theorem says that the equation, the original, the Pythagorean equation, is partition regular with respect to all pairs, which means that if you finitely color the natural numbers, then you can find x and y, which are in the same cell of the partition, and z is free, so z could be anywhere, so that x, y, and z satisfy the Pythagorean equation. You can also find x and z in some color, and some x in the natural number, so that the same equation is satisfied. And you can also do the same with y and z. But here, the pairs you find each time are possibly different. So in the first bullet, I say there are x and z, and here I say there are, sorry, in the first, I say there are x and y, and here I say there are x and z. But the first x with the second will, and in the way they prove the theorem, they will in general be different. So this is a genuine result about pairs. It doesn't say anything about triples. So for triples, I would like, for example, here my z to be also in the same color in CI. What I comment here is that they show density regularity, which is something better than partition regularity, but I didn't want to state the theorem in this generality. So now I'll get back to triples. And as we will see, the original question translates into a question about the measure preserving action of the multiplicative natural numbers. So I will give a couple of definitions in this slide, and then I will tell you what the theorem translates to. So a multiplicative action is a quadruple x mu tn, where you have a probability space x with a measure mu, and then you have tn being a measure preserving action of the multiplicative semigroup of natural numbers. So there is this classical device of Furstenberg called Furstenberg's correspondence principle, which says that a question about partition regularity or density regularity in the natural numbers, or in general in any group, can be reformulated in terms of a statement about recurrence in a measure preserving system. So if we employ this device here, Furstenberg's correspondence principle, we get that the conjecture about partition regularity of this equation, ax squared plus by squared equals cz squared, translates to the following ergodic theoretic statement. You want to prove the following: given any rado triple, if you have a multiplicative action and you partition the space x into finitely many pieces, then you can find x, y, and z in the natural numbers, so that x, y, z satisfy the equation ax squared plus by squared equals cz squared. And moreover, you have this recurrence phenomenon that a comes back to itself after time x, after time y, and after time z. So, so if one proves this theorem, then you have the original conjecture. Now, in joint work with Franzikakis, we proved the previous conjecture in the special case of structured actions, the so-called pretentious actions. So let me tell you why this is a nice result. Well, basically what happens is when you try to prove partition regularity for equations of the form ax squared plus by squared equals cz squared, or ax plus by equals cz, even in the linear case, when you try to prove partition regularity, or when you try to disprove partition regularity, you usually use some colorings called Rados colorings, which have very strong connection with multiplicative functions, and more specifically with pretentious multiplicative functions, which I will define in a bit. So basically, our theorem, which I will state in this slide, essentially eliminates the usual source of counterexamples for the conjecture. So let's give a couple of definitions. So we will denote by this calligraphic M the space of completely multiplicative functions, which are the functions of the natural numbers that are basically homomorphisms with respect to multiplication. And we note that the space of completely multiplicative functions is the dual group of the multiplicative integers. Now, there is a lot of theory regarding the space of multiplicative functions, and one very important theorem we have says that this space, you can decompose it into some part called the pretentious functions, which we should think about as the periodic multiplicative functions, and the aperiodic ones. And the aperiodic ones are the ones which average to zero along every arithmetic progression. So it's what a periodicity should mean, right? Now, given a multiplicative action and the function in L2, its spectral measure, you have the spectral theorem, which says that the spectral measure of f is a measure on the space of multiplicative functions. And we say that an action, so a system, is pretentious if for every function in L2, its spectral measure is supported on the pretentious functions. Namely, the measure doesn't give any mass to the aperiodic functions. So that's the definition for pretentious actions. And now I'm ready to state our theorem. So we proved that if you give me any Rado triple and any pretentious multiplicative action, then for any set of positive measure, I can find infinitely many triples which satisfy the given equation. And also you have the recurrence phenomenon that you want to have. Basically, you have that A comes back to itself after time X, Y, and Z, and you have also this quantitative lower bound, which says it's not only positive, but it's very close to mu of A to the fourth, which is the correct bound, I should say. Now, if you're given a general multiplicative action, Frantzikinaikis in a previous paper proved that the functions whose spectral measure is supported on the pretentious multiplicative functions form a factor of the system, which is called the pretentious factor. So our theorem essentially says that for any system, you have recurrence in the pretentious factor, and your recurrence is given by Pythagorean triples, generalized Pythagorean triples. So if one would like to settle the conjecture, what remains to be done is to prove that if you have functions in the aperiodic aperiodic regime, so they are orthogonal to the given to this pretentious factor, then some averages would vanish. Now, a couple of comments is that one, for those systems, for the pretentious systems, we prove something better than what the conjecture says. Namely, in the original conjecture, I didn't have this instance of A here. It was the measure of this triple intersection. Now, if you restrict to pretentious systems, you can actually do something better. You can add this extra instance of A in the argument of mu. This was something that the proof gave us, so we included it. And also, you may observe that here I prove something for any set of positive measure, while the original conjecture says something about partitions of the space. Of course, if you have something about sets of positive measure, you have the corresponding results for partitions of the space, because if you partition a probability space into finitely many pieces, one of the pieces has positive measure. So for those structured systems, you have those two enhancements of the theorem in some sense. I should say that in general systems, we know that you would indeed need a partition of the space. So, and in general systems, it's not, I'm not sure if you can add this extra instance of A. But the proof worked in our case for those specific systems with those less assumptions, so we included it. Now, as a consequence of our theorem, we obtain the following corollary. We can prove that given any radical triple and some collection of pretentious multiplicative functions, then for every arc around 1 on the circle, all of your functions visit this arc under times x, y, and z, which satisfy the generalized Pythagorean equation. And one could reformulate this into saying that we prove the original conjecture for a specific class of colorings, for the colorings that are generated by multiplicative and pretentious functions. Now I will do a sketch of the proof of the theorem in special cases. So I will describe what the tools are that we use. And if I have time, I will comment on what changes if you do not restrict yourself to, for example, finitely generated systems. So I will provide a sketch of the proof in the case of A equals B equals C. So when we deal with the classical Pythagorean equation, and also when my system is finitely generated. Now, finitely generated means the following. If you have a multiplicative action, the action is generated by the actions on the primes, right? Because every number can be written as a product of primes. So if you know the action of the primes, you know it everywhere. So the action is called finitely generated if the different transformations that you see when you only examine the action on the primes is finite. For example, if you go to each prime number and you say that TP is equal to this specific S, some S representing transformation, then you have a one generated action. So in this case, in general, the solutions of the Pythagorean equation are given in parametric form by x equals to mn, y equals m squared minus n squared, and z equals m squared plus n squared. So for any choice of m and n, those x, y, and z satisfy the Pythagorean equation. So I can, so I get that in order to prove the recurrence that I promised, it suffices to prove that for any bounded function which is non-negative and any epsilon, I can find infinitely many m and n, so that the integral of f times tp1 of f times tp2f times tp3f is greater than the integral of f to the fourth minus epsilon. You see that if here, in place of f, you put the characteristic function of a set A, you get exactly that mu of A intersect t to the p1 to the minus 1 of A, and so on and so forth, is greater than mu of A to the fourth minus epsilon. So it's the same statement. Now, I said I will restrict myself to finitely generated, and I will also restrict myself to ergodic actions. This is something that is not restrictive at all, restricting yourself to ergodic actions, because you can always use something called the ergodic decomposition, and basically without a loss of generality, you have ergodicity. So in that case, the spectral measure sigma f is supported on finitely generated multiplicative functions, and also pretentious, because I assume that I'm working with a pretentious system. So then, in order to prove the this inequality here, in general, in ergodic theory, what we do is we want to prove that we have some recurrence. So here, a classical thing to do is you average over m and n. You send, you take the averages to infinity. So you average over a square where one is smaller or equal than m and n, smaller or equal than capital N. Then you send capital N to infinity, and you see if you get convergence towards something positive. So here you have to average over a grid, not only over m and n, but over the grid qm plus 1 qn, where your averages over m and n are in boxes, so they are the classical additive averages, but you have to take an extra averaging over the step of the progression. The step is q, and those are multiplicative averages. So q belongs to something we call a multiplicative Fellner sequence. And now for when we do this, we want to use a spectral theorem. So I would like to see what happens for multiplicative functions when I take the same averages. And what happens is that for finitely generated and pretentious functions, multiplicative functions, we have the following concentration estimates. So the first one is this estimate by Klurman, Manzarel, Pohota, and Taravainen, which says that if you consider a pretentious multiplicative function on a geometric progression, on an arithmetic progression, and the step is q, then essentially the function is 1 over there, as long as your step q is very highly divisible. And then a generalization of this result came later by Franzignex, Klurman, and Moreira, where they basically generalized this to cases when instead of taking qm plus 1, which is a linear thing, you take quadratic things. So they proved that, for example, if you study your function, your pretentious function on qm plus 1 squared plus qn squared, then it is also essentially 1. So if we use 1 and 2, those two equations, and we also use a spectral theorem, which basically says that if you want to study the L2 norm of a function f in your system, you can study some L2 averages of its spectral measure. You can prove that TQM plus 1 of f is on average f, and the same happens with qm plus 1, when instead of qm plus 1, you put qm plus 1 squared plus qn squared. So using those two, we see that, and the specific forms of P1, P2, and P3, we see that we can essentially replace TP2F by F itself, and the same with P3. And for P1, which was 2mn, we insert the Q averaging inside, and we use the mean ergodic theorem, which says that when you have a multiplicative system and you take multiplicative averages here, then the multiplicative averages of T2Q and F will converge to the integral of F. So you arrive at this expression, and then by Jensen's inequality, this is greater or equal than the integral of F to the fourth. So this is how the finitely generated case is proved. So the proof is not very involved in this case of finitely generated systems. Now, when we pass to general systems, it becomes very technical. So do I have like 2 minutes?
Yes.
Okay. So in the general case, non-finitely generated case, the proof I presented doesn't work. The reason being, there are those Archimedean characters which cause problems. So we have to, instead of average over all m and n, we have to restrict ourselves to some specific set of m and n's. That's what I'm describing here, but I'll go a bit fast forward. And the real obstruction, the big obstruction, is by what we call one pretentious oscillatory multiplicative functions. And the problem is the concentration estimates are nice in the case of finitely generated multiplicative functions. If your function is not finitely generated, what the concentration estimates give you is much more cumbersome. So you can no longer average on Qn plus 1 Qn. You have to do some choice for some specific V and solve some congruencies, and also find some suitable factors to project your averages so that over there you get the recurrence. So I think I'll stop here. I won't get into more details. So the point is, in the general case, so in what we actually do in the paper, it's much more technical than the proof I presented, which is in the finitely generated case. So I'll stop here. Thank you.
Thanks, the speaker again. Any question to the speaker? So no question. So this is our last talk. So our second block of talks ends here. Our third block of talks will start at 9 a.m. US Central Time. See you then.